Number one says that in 1980, the population of a town was 5,000, and in 1990, it was 7,350. Assuming that the population increases continuously at a constant rate proportional to the existing population. All right, so this is what we're looking for, proportional, that it increases at a rate proportional to the existing population. That means if y is the population, then y increases according to some exponential function. And we're going to use the information that we were given to figure out c and k. All right, let's look at the first piece of information. The first piece of information is that in 1980 the population of the town was 5,000. So let's assume that we are counting from 1980. So we'll say t equals 0. The initial time is 1980. So when t equals 0, the population was 5,000. All right, let's use that information to figure out c. So we're going to just substitute t equals 0, and we have 5,000 is equal to c e to the k times 0. This is e to the 0, which is 1. So we have c is equal to 5,000. All right, so let's fill that in, 5,000 for c. The next piece of information is that in 1990, the population was 7,350. That is 10 years later. So when t is equal to 10, y is 7,350. All right, so let's substitute in t equal 10 now. All right, so we have 7,350 is equal to 5,000 e to the k times 10. And we're just going to solve for k. So let's start by dividing both sides by 5,000. And now let's log both sides to bring down this exponent. When we take the log of this exponential expression, we just get that exponent because log is the inverse of the exponential function. All right, so now we have what k is equal to, divide both sides by 10, 1/10 log of this number. All right, so let's just figure out approximately what k is equal to. All right, so with the help of the calculator, I get that k is approximately equal to 0.0385. All right, now let's answer the question, estimate the population in the year 2000. All right, since we started counting at 1980, so the year 2000 would be 20 years later. So we want to know when t is equal to 20, approximately what is the population? So now we know what our function is because we figured out what c and k are. So here's our function for population growth. Y is equal to 5,000 e to the 0.0385. That's our k, t. And now just substitute in t equal 20. All right, so that's what we're going to do now, t equal 20. And we have y is equal to 5,000 e to the 0.0385 times 20. And we'll just approximate this with the help of our calculator. And I have that after 20 years, the population is approximately 10,804. Number 2 says that the rate of change of a population of bacteria is proportional to the number of bacteria present. So that phrase tells us that we have an exponential function. Initially, there are 300 bacteria, so when t equals 0, y is 300. After 2 hours, when t equals 2, there are 750. How many are present after 5 hours? We'll start by substituting t equals 0. And we have 300 is equal to c e to the k times 0. All right, so we have 300 is equal to c. All right, let's look at t equal 2. Well, now we have y is equal to 300 e to the kt. We know that c can be replaced with 300. And now we'll substitute t equal 2. And when t equal to y is 750. So substituting t equal 2 and y is 750. And we have 750 is equal to 300 e to the k times 2. So we have 750 over 300 is equal to e to the k2, and now we log both sides. So we have the log of 75 over 30 is equal to k2. And k is equal to 1/2 log 75 over 30. Let's just approximate this with the help of the calculator. And we have the k is approximately 0.458. And we'll use this to answer the question when t equals 5, what is y? So now we have the function y is equal to 300 e to the 0.458 t, and we're just going to substitute in a 5 here and see what we get for y. Okay, and we get that y is approximately equal to 2,964. Number 3 says that a radioactive substance has a half-life of approximately 1,500 years. What percentage of a given amount remains after 500 years? So let's start by writing down our exponential function. And we're going to use the half-life that we were given to figure out k. All right, so let's suppose that we start with 1 gram of the substance. All right, c is always the initial amount. So let's suppose we start with 1 gram. Then after 1,500 years, we're left with 1/2 gram. All right, so we can use this to figure out what k is. So just take the log of both sides. And here we have k times 1,500 on the right-hand side. So we get k is equal to the log of 1/2 divided by 1,500. And let's just approximate what this is. All right, so approximating this using the calculator, we get that k is approximately this number. Okay, so I've rewritten the exponential function, replacing k with the approximation that we found. And now we want to answer the question, what percentage of a given amount remains after, here, what percentage of a given amount remains after 500 years? So let's just substitute in t equals 500. And we have y equals c. Okay, times 500. Okay, now this we approximate, and I get that this is approximately equal to 0.79. So we have that y is equal to c times 0.79. Now remember, c is always the initial amount. So after 500 years, we have 0.79 times the initial amount, or 79% of the initial amount remains. Number 4 says, carbon-14 dating assumes that the carbon dioxide on Earth today has the same radioactive content as it did centuries ago. If this is true, then the amount of carbon-14 absorbed by a tree that grew several centuries ago should be the same as the amount of carbon-14 absorbed by a tree growing today. A piece of ancient charcoal contains only 30% as much of the radioactive carbon as a piece of modern charcoal. How long ago was the tree burned to make the ancient charcoal? All right, and we're given that the half-life of carbon-14 is 5,730 years. Well, if we write down an exponential function, we can always use the half-life to find k. So let's start by doing that. So we're saying if we start with, let's say, 1 gram of the substance, then after 5,730 years, we end up with half a gram. All right, and if we log both sides, we'll get k. Okay, just divide both sides now by 5730, and we have that log 1/2 divided by 5730 is equal to k. Let's just approximate this. All right, so using the calculator, we have that k is approximately minus 0.000121. All right. So now we want to answer the question that says that a piece of ancient charcoal contains only 30% as much of the radioactive carbon as a piece of modern charcoal. How long ago was the tree burned? In other words, we started with a certain amount of carbon-14. So let's just say C is the amount of carbon-14 that we started with. Remember, C is always the initial amount. So we're left with 30%. So the amount that we have now is 30% of C. And we want to figure out what T is. How long did it take? How long is it since, or how old is that carbon? How long is it since the tree burned, or how old is that carbon? All right, so so this is the amount of carbon-14 today, and this was the initial amount, and we want to figure out what T is. So let's just write our exponential function with the k value that we found. 1 times t. And then we just have to solve this equation. Notice that we can divide both sides by c, so there's no need to find c to answer the question. Okay, we just divide by c, and now we are going to log both sides. Like always, whenever we have something in the exponent, that's what we do. So here we have ln 30 is equal to minus 0.000121 t. And we have t equal to ln 0.30 divided by negative 0.000121. And we expect this to, obviously it has to be less than 5,007, actually it has to be more than 5,730. Okay, because we're only left with 30%, not 50%. 50% takes 5,730 years. We're left with 30%, so we expect to get some number that's a little bit larger than this. Okay, so let's see what this is. Okay, so we get that t is equal to 9,950 years.